Is it all right if I scroll down to the cos one? So again, same thing for drawing your cos graph. You have your axes family. Cos of 0, well, that's your x-coordinate at 0 is 1. And then we draw arrowheads on the end to say that this pattern keeps on going over and over and over again. Can I scroll down to tangent? Not yet? Oh. So with tangent, wherever things are undefined, you have those asymptotes. So at pi over 2 and 3 pi over 2. I also went back and went to negative 3 pi over 2 as well. We still label our axes family 0, pi over 2 pi, 3 pi over 2, and 2 pi. So you know that tan of 0 is 0. You know that tan of pi is 0. If you wanted to add another point on here, you could add, you know that tan of pi over 4 is 1. You do now. You knew that all along. Which one? This is negative 3 pi over 2, negative pi over 2. Yes, there's a negative there. You just can't see it. It's one of those fancy negatives. There it is. It was a white negative, yes. Sure. And then I will give you marks out of 8 with the fancy white line in between the 0. So it's 8 out of 8. Oh! Oh! All right. So a little bit of highlighting now. So we take out our highlighter. And we can highlight some important definitions. Okay? First of all, something that repeats itself is called a periodic function. The length it takes for it to repeat is called the period of the function. So here we have the sine graph. What I don't like the scale that they used for the sine graph. That's why I got you to redraw it. But the period of our sine graph is 2 pi. We're going to have to explain all the characteristics of our sine graph. So if you're asked for the domain, well, since it keeps on going forever, we would say our domain is everything, XER. Where are the zeros of the function? Well, if we start labeling all the zeros and we start writing them down, do you see that you would have 0, pi, 2 pi? What would be the next one? 3 pi. And the next one? 4 pi. And can you see that that would keep on going? Yeah. And you also have negative pi, negative 2 pi, and that keeps on going. And you will be asked to write them all down. So how do we do that? Well, we look for a pattern. We notice that it's everything multiplied by pi, where the number in front are like 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, negative 5. If I put all those numbers together, what are those numbers called? Integers. So we write our zeros of our function as k pi, where k is an integer. So that allows us to write an infinite amount of answers down quickly. If you don't like that method, you can just write all infinite out. All right? The function has a maximum value of 1, a minimum value of -1, so that means our range is between -1 and 1. And that is our sine function. We could look at the same thing for cosine. Cosine also repeats itself once around the circle, so it also has a period of 2 pi. Cosine also has a maximum value of 1, minimum value of -1, so the range is the same. But the zeros of cosine are a little bit more difficult. And this is where your graph that you drew is better than the graph that they drew. Because where is our first zero? Our first positive one? Pi over 2. And then our next positive one? 3 pi over 2. If you went around the circle again, where would your next one be? 5 pi over 2 and then 7 pi over 2. This is a 2. And so on. And we also, if we look at our negative ones, we have negative pi over 2, negative 3 pi over 2, wow, negative 5 pi over 2. And so what pattern do you notice for the zeros of cosine? They're odd pi over 2. Does that make sense? Now that's not mathematical. We can't do this.
Why not?
Right? So mathematically, we need to come up with a way of showing something is odd. Again, I'm going to use the idea of an integer. So if I start with k as an integer, that's all positive and negative whole numbers, right? How would I make an even number? If I have all the integers, well, if I add 2 plus 1, I get 3. It's not. But 3 plus 1 times 2 gives me even ones. Does that make sense? You take any number and double it, and you will get an even number. And if you have any even number, and you add 1, you will get all the odd numbers. So the way that we write all the odd numbers times pi over 2 would be 2 times any integer plus 1 times pi over 2. So one way that you can write the zeros of cos is like that. And you have to define k, comma, where k belongs to the integers. 2k plus 1, because 2k makes something even, plus 1 makes it odd again. Or, so some people really like this pattern, the odd times pi divided by 2. The other pattern is based on sort of like coterminal. Okay? But if I start at pi over 2, what is the distance to go to there? How far is that from pi over 2 to 3 pi over 2? I'd have to add pi. Okay, think about your unit circle. You're at pi over 2. You want to go down to the bottom to 3 pi over 2. That's halfway around the circle. You'd add pi. And then from 3 pi over 2 to 5 pi over 2, that would add pi again. So another way that the zeros of cosine are sometimes written is like this. Start with pi over 2. That includes this one right here. Good. And then we can add or subtract pi as many times as we want. If I add pi once, I'd get to the next one. If I'd add pi twice, I'd get 2 down. If I subtract pi once, I'd go back and get that one, where k is an integer. So you have 2 choices. And if you wanted to, in the first one, distribute the pi and simplify, you would get exactly this again. Question?
So, if you get one of these graphs, is it ever going to end, or is it always going to keep going forever? Because the circle.
The circle keeps going forever. Sometimes you'll get a question, though, that says, consider the sine graph only from 0 to 4. The domain then, like this one, the domain is everything because it goes on forever. But if they stopped it from 0 to 2 pi, then they would say 0 to 2 pi. Okay? And for most of the trigonometry you've done in grade 10 and 11, you only looked, well, in grade 11, you went from 0 to 2 pi. You went once around the circle. In grade 10, you went from 0 to 90 degrees because you were just doing SOHCAHTOA and you didn't have angles bigger than 90 degrees. The good old days. Can we bring back the good old days? Yeah, every once in a while we'll bring back the good old days. We'll do some math from.
Ruin the good old days with some more math.
Math is awesome.
So the way that your textbook has written them, they've done the odd number times pi over 2. The first way that we looked at it. But you can choose. If you like, hey, this is one that I know's on there, and then I add k pi, which is a little bit more similar to the sine one, right? The sine one was just k pi. And all that's happened here is we've shifted it pi over 2 to the right and have the same ones. In fact, the sine graph and the cosine graph are the identical graphs, just one is a transformation or a translation of the other one. Few more important things to highlight. The definition of amplitude of a sine graph or a cosine graph is the distance from either a maximum point or a minimum point. So in the textbook, they've shown the distance from a maximum point to the center line. And off to the side, I'm going to give you some other definitions of, or synonyms of center line. Sometimes the center line is just called the average, and sometimes it's called the sinusoidal axis. So the center line, and when we graph our center line, we're often going to graph our center line like an asymptote with a dotted line, because it's not actually part of the graph, but it helps us graph it. So we'll graph it with a dotted line. Our job now in the next couple of questions is to find out how do each of the transformations specifically affect the characteristics of a sine and cosine graph. Not so much the tangent graph. We're going to look specifically at our sine and cosine graphs first.